Attitude, determination, and control systems. The endless expanse of space waiting to be explored. Should be easy, right? Just launch a rocket and use some directional burns to adjust the flight path. But wait, how do we know in which direction we have to go? And how do we even turn the rocket towards that direction? Well, these questions can be answered by using an ADCS or AOCS, which stands for Attitude Determination and Control System or Attitude Orbital Control System. This video will be limited to navigation on and around Earth, since this suffices to give a reasonable introduction to the subject. We'll begin by defining a concept which is widely used in aeronautics: reference frames. Oxford Languages defines a reference frame as a set of criteria or stated values in relation to which measurements or judgments can be made. In short, we can define an environment in which we can measure things. Imagine an object whose length is unknown. Using a ruler as a reference frame, the lines on it being a set of measurable coordinates, you can determine its length. The ones used are often depicted using a three-dimensional Cartesian coordinate system, which can be seen as a three-way ruler. There is a set of multiple defined reference frames, which are optimized for use with satellites and other spacecraft. The spacecraft body frame, also known as SBF, is a fixed reference frame whose origin often lies in a specified point of the spacecraft, for example, the center of mass. This frame is often used to align components in the satellite and to represent the actual satellite in space. The Earth-centered inertial frames, or ECI frames, are commonly used frames for operations around Earth. Their origins are in Earth's center of mass. The most used one is the ECI J2000, which is based on the mean equinox at 12 o'clock terrestrial time on January 1st, 2000. The x-axis of the frame is aligned with the equinox. The z-axis is aligned with the Earth's rotation axis. The y-axis results from the previous axes. The Earth-centered Earth-fixed frame, or ECEF frame, is similar to ECI centered on Earth, and its z-axis is also defined by the Earth's rotation axis. Unlike the ECI though, it does follow Earth's rotation. This is achieved by defining the x-axis over 0-degree longitude, which is the prime meridian, on the equator. The y-axis then results from these two. This one is commonly used for tracking satellites in relation to Earth locations, for example, satellite navigation. Let's continue with a very important mathematical concept: quaternions. Quaternions are a number system which extend the complex numbers, and explaining them fully would be long enough to fill another video of this length. So I will just explain the parts relevant for aeronautics and how to use them. Quaternions have multiple valid representations, but since the Hamilton representation is preferred for aeronautics and space usage, I will be using that one. In the Hamilton representation, a quaternion consists of four numbers: h equals a plus bi plus cj plus dk, also referred to as w, x, y, and z in this video. Basically, this number system is four-dimensional, using a real axis and three imaginary axes. Since three-dimensional number systems don't satisfy general algebraic functions, a four-dimensional system has to be used, since multiplication is possible for this one. The real part is often called the scalar part, and the remaining three are often called the vectorial part. But you have to be careful, since it doesn't really represent a vector. To get a feel for how these parts relate to 3D space, we can take a look at directional cosines. The directional cosines of a vector are the cosines of the angles between the vector and the base axes, so in our case the x, y, and z axis. They can be integrated as follows. For the rotation to be valid, a quaternion has to be a unit quaternion, so it must fulfill the following condition. These quaternions and quaternion rotations can be easily applied to a quaternion V by multiplying the rotation quaternion Q as follows. A 3D vector can also be rotated like this, but you have to convert it to a quaternion first by using 0 as its W value. Q star is the conjugate of the quaternion Q. The conjugate of an element Q is defined as follows. The multiplication of the quaternions can be performed by using the Hamilton product. The Hamilton product is defined as follows. For making calculations, you have to make sure to apply the complex numbers and quaternion-specific rules as follows. To make handling quaternions even easier, there is another rule, where the rotation of a product of two quaternions, Q1 and Q2, is the same as rotating by Q2 and then Q1, since the following transformation can be made. This all looks a little bit uncomfortable to deal with, so why are we using quaternions and not just the Euler angle system we all know? For one, the Euler angle system is prone to something called gimbal lock. This occurs when two axes become identical, which loses us a degree of freedom. Another reason is computation time. Calculating with quaternions requires less computation steps, making it the preferred choice in engineering, video games, satellite applications, and other real-time applications. The groundwork for these quaternion rotations was laid by Euler in 1775. This is called Euler's rotation theorem. It states that in 3D space, any displacement of a rigid body, such that a point on the rigid body remains fixed, is equivalent to a single rotation about some axis that runs through the fixed point. Attitude representations. Of course, the spacecraft always has an attitude, but how we represent it depends on our requirements and knowledge. The following systems are the most known representations that can be used. Euler angles. This is probably the most widely known and intuitive of all these representations. Here, the attitude is represented by a chain of 3 rotations around 3 perpendicular axes. Most commonly, these axes are referred to as the x, y, and z axis. Of course, using this representation comes with a few drawbacks. For one, you need to specify the order of the representation, meaning you have to specify which axis is rotated at which point. As you can see in this 3D modeling and animation program, the chosen representation of the model's rotation is XYZ Euler. This is the case because not a lot of computation is required and the user needs an interface that is readable and intuitive. Euler axis angle. This representation uses 2 components, a vector along the rotation axis and the angle describing the magnitude of rotation, which is usually theta and e. Rotation vector. Usually, this representation is just used for analysis, since it is convenient to have both angle and axis in a single vector. This representation is equal to the Euler axis angle representation, but in the following form. And finally, quaternion. This is the most widely used and efficient representation. As we got to see earlier, it can seem confusing at first, but it is invaluable for its advantages. Attitude kinematics. In physics, kinematics describe the motion of bodies or points in space without accommodating applied external forces. For the satellites or SBFs we are considering, attitude kinematics describe their ongoing rotation. An example of this would be an Earth observation satellite, which needs to rotate at a specific rate to stay pointed at Earth. But how do you achieve this? Well, based on the attitude representations, we can calculate the necessary derivatives to use for integration, which in turn provides us with the attitude at a desired time t. Of course, all the other representations we did and didn't talk about have their own respective kinematics parameterization, but the quaternion one is the most relevant for use with spacecraft. Attitude dynamics. Since attitude dynamics itself would be extensive enough to fill its own video, we won't go into too much detail. Attitude dynamics, in contrast to kinematics, deals exclusively with external forces on the object. The first instance of dynamics that comes to mind is, of course, gravity. Gravity is the reason why we can have orbits as we know them in the first place, and is the weakest out of the 4 fundamental forces in physics. A way to abuse this force is, for example, a gravity gradient stabilization system, which we will go over in a bit. Another one that quickly comes to mind is, for example, solar wind, which is radiation pressure from the sun. This can also be abused by solar sails. But how is all this put into practice? Well, the system can be separated into 2 components, the ADS and the ACS, which stand for Attitude Determination System and Attitude Control System respectively. Let's go over attitude determination systems first. Attitude determination is done using sensors and can be realized using multiple methods, each with their own strengths and weaknesses. Most common sensors can be separated into 2 types, relative attitude determination and absolute attitude determination. The most common relative attitude determination sensors are gyroscopes and motion reference units, also known as IMUs. The most common absolute attitude determination sensors are horizon sensors, orbital gyrocompasses, sun sensors, earth sensors, star trackers, and magnetometers. The most commonly used absolute attitude determination sensor is the star tracker, since it is more precise than an earth sensor or as a sun sensor, but the latter still has some applications due to their low cost and reliability. To go into a little more detail, the star tracker consists of an optical device which captures images and compares the results of an image processing algorithm with data from a database of known stars. The database commonly consists of around 50 to 60 stars, which is sufficient for most missions. If higher precision is needed, a large database is put to use, which contains data of multiple star fields. Usually, the image processing works as follows. First, the image gets corrected for distortion and gets smoothed out, followed by a Gaussian blur to get rid of noise. What follows is a simple gray conversion and a binary conversion, turning the image black and white. This makes the image easy to analyze. Also, it is common in this step to adjust the brightness of the image to a point where the number of detected stars matches an estimation of how many stars should be in the field of view based on the density and distribution of the stars in the database. Next, an edge detection algorithm is run over the image, usually canny edge detection, which reduces information on the image and speeds up the process. Finally, a contour detection algorithm is run, which marks out all detected stars. The end result is the final position of all stars detected in the field of view of the optical device, which then can be compared to the aforementioned database. Now that we have data to go off of, we can make an estimation of our attitude. For this, we can use multiple methods with different advantages and disadvantages. For one, we have static methods, which do not use all data. For example, the Q method, Quest, TRIAD, or SVD, which stands for singular value decomposition. Then there are sequential methods, which do use old data, like the Kalman filter or the extended Kalman filter, which is usually used. These use data from previous iterations to calculate a more accurate attitude estimation. For time reasons, I will only go over the simplest method here, the TRIAD method. TRIAD considers two measurement vectors, for example, from the sun sensor and from the Earth sensor, which we call SB and EB here. B stands for in relation to the body frame. We also have two known components, SI and EI, which are the exact same vectors but in relation to the inertial frame. Following the basics, we can now start to construct the triads, from which this method took its name. For the first component, we take the most precise vector we have measured and its inertial counterpart. The second component is calculated as a normalized vector perpendicular to SB, which is determined by the vector product of SB and EB. The third vector is calculated over the vector product of the previous two vectors. That way, we now have two vector bases with the following relation. And we can extract the rotation R. Of course, we can use this rotation matrix as a quaternion by first extracting the vector over which we rotate. We can do this by finding the eigenvector for eigenvalue 1. The vector u can now be treated as follows. This is our axis of rotation. The angle of rotation can then be calculated by determining the trace of our matrix. Since a change in base doesn't change the eigenvalues of our matrix, we can represent the rotation as a rotation over the z-axis of our new base, which is now equal to u, and represent our trace as follows. The angle can then be determined by solving for theta. Using our preparation, the vector and the angle, we can now determine our attitude quaternion Q. Now for attitude control systems. Attitude control is done using actuators and can also be done using multiple methods, but the most common is a PID controller. The controller applies a control torque T on the spacecraft using actuators, which is dependent on the current error E. The PID parameters Kp, Ki, and Kd need to be tuned according to simulations, of course. The resulting torque can then be applied by a wide variety of actuators, which include but are not limited to the following. Thrusters, spin stabilization, momentum wheels, control moment gyros, solar sails, gravity gradient stabilization, magnetic torquers, and pure passive attitude control. I hope I was able to give you a good overview of attitude control and determination systems. I gave you an overview of the mathematical basics, different representations of said attitude, and how to deal with kinematics. I showed how the satellite knows its attitude by using sensors, different methods of determining it, and how the desired change in attitude is realized. I hope this video was helpful for you, and thank you for watching.